Okay, let's see. It's gonna be sequential digits. Right. Medium, an integer has sequential digits if and only if each digit in the number is one more than the previous digit. Return a sorted list of all integers in the range low and high inclusive that have sequential digits. Low and high, that's a lot of possible values. Sorted list. Interesting. Huh. I mean, 10 to the ninth. I assume they... Okay. The bounds don't actually compare to the actual number of values. I guess there's maybe log of 10 to the ninth. Hmm. Yeah, I feel like it's something like log of 10 to the ninth is... No, that would just be 9, right? What is the scaling for the number of sequential digits when the bounds are n? Hmm. Feels like it would scale with log of n, but then that would just be 9. Maybe it scales with like square root. Square root of 10 to the ninth is still, I guess that's 10 to the fifth. Okay, maybe square root. Okay, so how to find, actually, yeah, it might be a log. Huh? That's not a lot of numbers. Um, okay, so the lowest stuff is always going to be starting with, no, it's starting with the no, lowest number of digits, huh? Lowest number of digits. I wonder if I should do a sorting. Do. This feels like backtracking, maybe actually. Backtracking with an array. No. Backtracking with, how would I even do this? Backtracking. Um, I could, I think the fact that it has a lower bound that's not just one makes it a little tricky because I have to, if I just do like one up to the high value, it's actually slightly easier to formulate the process instead of um, an arbitrary low value up to the high. I guess I should just start with just assuming that low is 1 and then see where that takes me. Hopefully I can kind of recover from that or modify from that. Okay, I think I'm going to go ahead and create like a function that maybe takes a starting value, starting. So what is this? What is this doing here? 1, 2, 3, 4. I could just try sorting, to be honest. It's not going to be very many values in the thing. Try sorting. How many values are there going to be? Like, I think this might be just a pre-compute 10 to the 9th. There's like 9 values that are 1 digit, 9 that are 2 digit, 9 that are 3 digit, or at most 9, right? 4 digits is not even 9, it's 6. So it feels like this might be actually a pre-compute, like pre-compute all the actual sequential values and then just use like binary search to find the appropriate indices where the low and high occur within that sorted list, and then just like return the sliced answer within that subset, slice subset array, subarray. Okay. I'm gonna say that's gonna be like at most um, like 45-ish, 45, yeah, n squared divided by 2. If there's like 9 single digits, actually you can't even have single digits. It's gonna be 89 is the biggest 2-digit sequential, right? So it's like 8 2 digits, 7 3 digits, 6 3 digits, and then like 1. Actually, there's not even 1 because 10 to the 9th is smaller than 1 2 3 4 5 6 7 8 9. Yeah. So honestly, this thing I could pre-compute it using. I could literally type this out probably faster than um, than coming up with the code to generate this. Unless I use like a AI for it, which makes some sort of sense in some world. Um, do okay, so let's go ahead and just not do that. For let's say this every starting digit in range from 1 to 10, or 1 uh, 1 to 10, I guess. No, it literally just cannot have a starting 9, right? So it's 1 to 9, not inclusive of 9. Let's say I have an array of all sequential values. It should go up to 9, unless it starts with 1. I guess I should probably want to make this a backtracking function. Say I have a value that's the current value and the last digit, the ones digit, and this is going to return, this is not going to return anything. So value go, the next value is going to be the current value times 10 plus the last plus 1. So if the last digit is 1, then this is going to be 1 times 10 plus 2. So that'd be 12. All sequential append this value. And then if the next value does not equal, I guess if this last value doesn't equal a 9, I'm good. Then I want to backtrack further. And then for every starting value in the range of 1 to 9, backtrack starting with that value. Okay, let's see what this gives me. Okay, this was roughly good. Let's go and sort the all sequential. Yeah, why is there double zero? Why is there double zero? 8, 9. Oh, I think this might be if the last value shouldn't be 8. Yeah, whoops. Okay, 1, 2, 3, up to 7, 8, 9. Okay, 1, 2, 3, 4, up to 6, 7, 8, 9. Okay, and then technically this is too big, but whatever. All right, so I have my all sequential. I'm gonna go ahead and insert that here. And I'll go ahead and just this for reference. And then I'll just find the indices that are appropriate. So it's the bisect left, I believe. Bisect binary, searching for like 10, finding where 10 would insert, the index where 10 would insert within that. So I'll call it index 1. Index low is bisect left. The array, which is all sequential. The value I'm searching is low. And then index high is bisect. I want this bisect right, bisect left. I think I want this bisect right. And then I think I want to return the all sequential splice or sliced from index low to index high. Okay, I just need to make sure I have some test cases that cover like the actual bound edge cases where it touches the sequential values. So let's say low is going to be 23, high is going to be 7, 8, 9. Okay, yeah, works. Cool. All right, pretty straightforward. Technically, technically I could have just written that all out. That was like, what, maybe 40-ish values within that, all sequential pre-computed values, 40-ish values. Mm. All right, summary. So would have done this in a few ways. The set of all, or the list of all kind of sequential values, even for kind of 10 to the ninth, is not that long. So could have just typed it all out. But in the spirit of the problem, used a backtracking function. It's basically like a kind of a mini recursive function. Mini, kind of a recursive function, really. To generate the to generate a list of all values, then sorted that value, then sorted those values. To generate a pre-compute list, use that pre-computed list along with searching for the appropriate low and high indices using bisect. The bisect function, and returned the subarray within that to for the answer. So for backtracking functions, generally it's like pass in some sort of intermediary value. You do something with it, and then maybe add that kind of value to your answer, or in this case, your pre-computed all sequential values array. And then if necessary, you backtrack further. In this case, backtracking further is just going one extra digit onto that. So this is starting with a single digit, not including 9 or 1 through 8 inclusive, because from a ones digit, the lowest thing is going to be a 2-digit value, and so you can have like 1, 2 up to 8, 9. So anyways, backtrack calling that value, make that into like an extra tens, move the decimal over, add in the next digit onto it to make it sequential, append that intermediate value to your list, backtrack further if it's not like adding at 9. And then once you have that pre-computed, kind of sorted, printed out, then that was copied here, and then just use bisect left and bisect right to find the indices to slice your array to return the answers. Time complexity, this can be O of 1. It's O of log k. Search for the appropriate indices. The backtracking function, which technically is part of the pre-computation, took O of So let's say it's d squared, where d is the number of digits in the largest value, which in this case d is equal to log of n. So in theory, you could simplify this to be O of like 2 log n or O of log n. Because if you do like, actually, is that right? No, that's not right. Poor math. It'd be like log n squared. O of the quantity log of n squared, which is not the same thing as O of 2 log n. That'd be log of n squared, log parentheses n squared, close parentheses, is 2 log n. Anyways. Because that's the number of things in it. In practice, this is very close to just O1. Base complexities can be O of, yeah, well, same as the size of O of log of d squared, where d is the number of digits. All right, cool beans.